Hello everybody, today we are making a presentation on the nozzle geometry effects and on aerial water dispersion. I'm Getik Memoria and this is
Orveshlia.
so moving forward, quickly going over the test objective. This experiment is to evaluate how internal nozzle core geometry affects flow rate and dispersion in aerial water dumping applications through physical testing. So, some background and prior work, what exists in the field before we conducted these tests. A commonly used aerial firefighting system called MAFS uses a modular water dumping nozzle. These are usually fitted to military aircraft to increase firefighting and fire suppression capabilities really quickly. Prior work related to nozzles has primarily been focused on sprinkler and fire hose designs used in structural firefighting. So MAPS is kind of a one and only system that's specifically designed for aircraft fire suppression. There's a very limited published work available on the MAPS nozzle internals because this is a military and firefighter project. So and it's one of a kind. So there's not a lot of resources available to understand how this works. How is our approach different? Well, the biggest thing we're trying to do is physical testing of MAF inspired and alternative nozzle geometries. We have four primary designs that we are testing. It's a shell, a poppet valve style system, a standard MAF system, and our modification to the MAF system. Use of 3D printer and image-based dispersion analysis will help us quantify and qualitatively understand how the flow rate and dispersion change based on nozzle geometries. Nobody has ever conducted small-scale physical tests of MAF nozzles, so we thought it would be interesting. Why this matters? Well, due to climate change these days, wildfires are increasing in frequency and severity, like the example we've seen in California earlier this year. That was actually our primary inspiration to pursue this project. Even small design improvements in nozzles can increase the water coverage, reduce waste, and improve fire suppression efforts. We are currently dealing with water scarcity issue as well as a heat wave that both compound and make fire suppression very difficult. So our theoretical model was based on Torricelli's law that was used to predict flow velocity through the nozzle. This helped us understand basically what our flow through our nozzle could be like and helped us size our test setup. Because if our test setup was too small, we wouldn't have enough steady state data to understand how the nozzle behaved. And if our test setup was too big, we would waste a lot of time conducting these experiments. The dispersion through the nozzles was assumed to follow typical exit jet behavior and under turbulence effects. So this is standard practice used by many theoretical papers to quantify dispersion when as flow moves through a body. So our physics-based results based on Torricelli's model is used as a baseline to, like I said, predict performance and size our test setup. Flow rates and dispersion areas are estimated and compared to the data we collected during our experiments. So our experimental test plan is designed to isolate the nozzle core geometry effects from environmental and fluid effects. So to do that, we started with a fixed height hydrostatic setup, which is a bucket with a 3.5 gallon capacity, and that's filled up to water column height of 2.228 meters. 3D printer nozzles are used under identical conditions. It's the same bucket, it's the same fluid. Emptying time, flow rate, and splash area are then recorded to understand flow behavior and dispersion behavior. Our experimental setup is a quick diagram. There's the water column, there's a nozzle, we have a grid for measuring the dispersion patterns that help us quantify the area at which the flow spread out. So each grid square is about 1 centimeter by 1 centimeter big, and using slow motion footage, we can capture the first few seconds of the water hitting the dispersion graph paper and understand the area that is taken up by the flow. The water is also dyed in a distinct red color that helps us identify the pattern as well. So the design of experiments is pretty straightforward. Our predictions were based on our general understanding of fluid dynamics throughout our time at Clarkson. We believed the shell would have the highest flow and would have moderate spread. The poppet valve, which is kind of designed like a fire sprinkler, would have the lowest flow but would have a conical spread and would have the highest dispersion area. The match system would have medium flow and narrow targeted spread, while the modifications we made to the match system would increase the flow and give us a tighter spread for precise water delivery.
So now I'll be going over some variables and controls that we took into account. So our independent variables for this experiment were nozzle geometry. Our dependent variables were the flow rate, dispersion area, and the emptying time. And then our controls were the water height and the nozzle inlet diameter. So for measuring techniques, we used a stopwatch to record the time, calibrated fixed volume container, and a slow motion video from a camera to record the dispersion pattern, and then graph paper for measuring the splash footprint. So for the equipment used, we had 3D printed nozzles made from IPLA. We had a water bucket, which consisted of 5 US gallons of water. We had digital thermometer for temperature. We had a stopwatch. We used an iPhone to record, and we had a dispersion grid. So considering calibrations and standards, water column calibrated with a lab beaker and a fill line marker, consistent nozzle mounting, and water fill line checked, room temperature and water temperature recorded for each test. So for the budget, you can see all our costs came out to be around $50. Half of it was for the 3D printing that was already provided us to by school, and then some of them were things that we bought. Risk assessment, so there's always risks with every experiment. So for this, avoid regions with electrical connections due to splash risk. Sharp 3D printed objects, for them use gloves and sanding if necessary because they can pierce through your skin. Avoid lifting strain by using hoses to fill up water column. So for results, you can see the numbers here. I'll be going into further analysis on the next slide. So result analysis. So the shell nozzle had the highest flow and the moderate dispersion. Poppet nozzle had the lowest flow and the highest dispersion. MAFs balanced but focused jet. Modified MAFs near maximum flow with tightest dispersion. Uncertainty analysis, so there is a certain error of margin that you have to take into account for. So for the volume fill mark, like a plus minus 20 ml error. For temperature, a plus minus 2 degrees centigrade error, and then observed flow rate variability 0.15. So concluding this presentation project, the geometry of the core impacts both flow rate and dispersion pattern. Poppet nozzle trades flow efficiency for a wide coverage. Modified MAFs offers flow efficiency and precision delivery for targeting fire sources and small fires. Errors and their implications. So in the real world, airflow effects from in-flight environment were ignored here. 3D printing paneling could slightly impact the flow behavior. Definitely useful for future nozzle design influence. So for future work, expand testing using variable fluid pressure, test in wind tunnels for stimulated flight airflow, and explore combinations of flow and dispersion-focused features. We'd like to thank everyone for helping us with this class, specifically Professor Hoover for providing us with the sources and the knowledge to move ahead with this project, and Todd for providing us 3D printing expertise and last-minute help with everything. Thank you.
Thank you.